Giuseppe for the invitation to come and speak here. This is a really wonderful opportunity, especially for me that since October 7th, I canceled most of the conferences I was supposed to come. So it's a really great joy to see you all here and be together, and a bit of escapism. So as Lorena said, we research in our lab cancer in general, and we use different tools, nanotechnology, 3D printing, and others to look at it as a multidisciplinary field where we need every possible player to take a part, whether they are the clinicians, and I am in the medical school, probably the only chemistry lab in a medical school in our building. And we have engineers, chemists, biologists, even one architect, because she's dealing with all the planning for the 3D printing. So I will show you one example how we use this 3D printing to print models of cancer that mimic better the clinical scenario. And the reason that we wanted to do that, I'm sure all of you are familiar with this green chart showing that it takes about 10 to 15 years to develop a drug. It's, the attrition rate is outrageous. No other field will accept anything like that, starting from 10,000 molecules in either by bioinformatics, computational chemistry, or actual work on the bench, narrowing it down to several, like 10, 20 candidates, then taking it to the clinic, and only one of them will be actually approved at the end for clinical use. So starting from 10,000, one single product at the end after 15 years, and not enough that, it also is very expensive. As you know, it costs about $2.6 billion if you take all the failures included, but even if we take them out, it's $1.3 billion to develop one drug. And we have to be very conscious about it, even ethically or morally. And if we think how much it costs to build a whole hospital compared to drug development, it costs about $200 million to build a whole hospital. And if we take it versus one drug, how many people can we use? Can we help with each one of them? We have to be very conscious how we improve this. And what's the reason that this attrition rate is so bad? And it's not similar like other fields. If we take high-tech and computing, you're used to see the Moore's law, where the faster, the better the computer power, it goes, the cost goes down. Here, it goes down, but what goes down here is the number of drugs approved per $1 billion investment. So we're not doing great. And one of the reasons that we thought about, and then we found this data from companies and from translational clinical trials, that the problem sits around the models. The models we are using, thinking that we can isolate only cancer cells, and I'm talking about oncology, but it's true for all the other fields that we can think of, thinking that we can isolate just the cancer cells, see them on a plastic rigid dish, without the microenvironment cells, without the vessels, without any hemodynamics, without flowing vessels, let alone. Sometimes we co-culture them with endothelial cells, thinking that we have some tubular structures there. They have no lumen, they are not connected to any pump, and there is no flow there. And they are not in 3D. There is no extracellular matrix, so a lot of things are missing. And actually, when I think about all that, I think that it's a miracle that even some of the drugs are translated at the end to clinical use and are doing pretty well. So if we look at the numbers, 70% of drugs are toxic in animal studies and will not be toxic in clinical trials or in humans in general, and vice versa. It could be that they will not be toxic in mice and will be toxic in humans. This number, 77% of pharma studies cannot replicate what we do in the lab, in the academic labs. And it's not because anyone is cheating, I hope so. It's really because we're using different conditions, we're not detailing all the conditions, we're not working under sterile condition where it's not GMP, and then things do not translate very good, and the numbers, again, 75% according to Bayer from their studies, 89% in Amgen, and these are only two that I managed to get the data. 30% of cell lines are misidentified. So all of you that got questioned while submitting a paper, did you authenticate the cell line? There is a reason for that, and we published it recently, a year ago, where we see the differences in the proteogenomic signature of cells that we co-culture for 3-4 decades, and we assume that they are the same, and they change. And if they change, it means that they will respond differently to drugs. So the way they responded to drugs in my lab will be different in another lab that are using the same line that we bought from the ATCC, but we won't get the same results. 25% of the antibodies target wrong protein. I was really happy to see that because I thought it was only an affair between me and Santa Cruz. So it's not only in my lab, it's in other labs as well. And 20% of complex drugs are misproduced because we are synthesizing things in, at best, at least in my lab, at best it's 1 gram, 2 gram. We never get to the kilogram scale, and many things happen. If you like to cook or to bake, you know that it's not just doubling the amount that works the same. There are so many expertise that are taken for scaling up a product. So in general, if we look at all the fields, all indications, the likelihood of approval of a compound that enters phase 1 is around 8% to be approved at the end. And for oncology, which I will focus on today, it's about 5%. So for every 100 compounds that we take to phase 1, only 5 will actually make it. So at that point, when we started to think how we can design better models, better cancer models, we were not the only ones. There was a year ago, the FDA published and the US Congress signed this Bill of Modernization Act 2.0, which means that we need to find alternatives to animal testing, not only because of the animal liberation front, but which is important, but also that it will be really relevant clinically. So the way we approached this was to start working with our clinicians. As Rena mentioned, we are affiliated, our medical school is affiliated to 17 different hospitals in the center of Israel. And we get notifications from the neurosurgeons that there is a patient with, let's say, a glioblastoma or brain metastasis. We get the MRI, we do the image analysis, we convert the file to a 3D printer, to a STL file, and on the day of the surgery, we get a piece of the tumor and the blood, and we create cell suspension. We 3D print it according to the MRI, together with the blood vessels, and the blood vessels are printed with a different gel that is a sacrificable gel, like pluronic or carbohydrate. And inside it, there are the endothelial cells and the pericytes, and we create these lumens that are perfusable. We connect it to tubing, to microfluidic tubing, and to a peristaltic pump where we can flow through them. The blood, meaning blood that we get from the same patient, so it fits, and it's relevant to have to test immunotherapies where we cannot do it when we use a PDX, a patient-derived xenograft, taking a human tumor and implant it in mice that are immunodeficient. So there is no relevancy to test anything that is concerned, like nanovaccines that we design. I will not speak about that today, but it is published, or any nanomedicine that is related to stimulate the immune system makes it irrelevant. So when we published that paper, Nature Reviews Cancer asked us to give some background to the field of 3D printing for cancer modeling, and we saw that actually it's a young field, it's around a decade, and it went very systematically just by printing the cancer cells, then separately other labs were printing just the endothelial cells, trying to create a grid like as you see here, and so on until we got to this that still is not perfect, but at least we have branched vessels that flow through the tumor and flow the PBMCs, the peripheral blood mononuclear cells that are isolated from the blood of the same patient. And we can use it for many things. This is just some ideas, looking at the gene expression, single-cell RNA-seq, whole exome sequencing, RNA-seq, proteomics. We did on this by degrading the matrix, the hydrogel that we synthesized that mimics specifically the organ where the tumor comes from. We can look at cell-cell interactions. And we can follow, if it is perfusable, so we can flow through them, the nanomedicines that we synthesize in the lab, and see if indeed the EPR effect exists everywhere. And many times we'll see that it does not exist. In many tumors, it's not that it doesn't exist. There are blood vessels that are recruited to the tumor. There are angiogenic blood vessels. They have the same characteristics that we think that they are hyperpermeable, but it's only in the viable rim and not inside the tumor. So assuming that the nanomedicine will penetrate all the depth of the cancer tissue, and again, I'm speaking about cancer, similar to any disease tissue that you will think of, it's a challenge, and we can follow it by confocal microscopy that we run during the evaluation of the efficacy of the nanomedicines that we synthesize inside those models. And we can look at it by either to design this high throughput system. It's like on a 96 well plate where we print 96 mini tumors, like mini avatars of every tumor. And then we can use it for like high throughput screening for personalized therapy, for target discovery, and for drug development. So if someone has 10 candidates that they want to select the lead compound, we test it and we see which one is the best to go ahead forward to clinical trial phase 1, or if they have already a lead compound, to see to which indication would be best to start with. So this hopefully will increase the likelihood of approval at the end. So this is how it looks. It's a very busy slide, I know, but we start with the polymer chemists and the engineers in the lab. So they synthesize the different hydrogels that mimic each one of the organs. The engineers look at their rheological properties, whether looking at young modulus, at stiffness, swelling, elasticity, plasticity, anything that you can think, because it affects, again, the proteogenomic signature of the tumor cells. So if we take a tumor from the brain, as I mentioned, like a glioblastoma or brain metastasis, and put it in a hydrogel that mimics much better the skin or a bone that is much stiffer, they will change completely, and the results that you will get will be different from what will actually happen in vivo or in a clinical scenario. So for each one, we have the gel that fits. In the case of the brain, we published one of the hydrogels that we created that is based on fibrinogen, fibrin, collagen, on transglutaminase and thrombin. And again, all this is published. You can find it there. And this is a blue brain, but inside, if you go deep, 17 hours of scanning by confocal microscopy, you can see that there is a blood vessel that we printed with pluronic, and the cells, the endothelial cells that are in red here, and the pericytes, again, isolated from the tumor that we got, as I mentioned before. And we printed, and you can see by a Z-stack here, that there is an actual lumen, and they surround, the endothelial and the pericytes surround this lumen, because we are liquefying the pluronic by different temperatures to get rid of it, and then flow the PBMCs from the same patient. And you can see that within a month or 2 months, we can keep it alive, and it has a life of its own. It starts branching, connecting, creating anastomosis between different blood vessels that we printed. And we can see that the flow becomes more and more branched if we follow it by dextran Fitzy, for example. And we can also test immunotherapies, which was one of the most important aims for our labs, because we synthesize a lot of nanomedicines targeting the immune system, nanovaccines, and other immune checkpoint modulators. And what you can see here is a PDL1 small molecule that we designed by CAD, by computer-assisted drug design. And we encapsulated it in a PLGA nanoparticle, and we wanted to see if this specific patient, a melanoma patient, will be predicted to respond to this PDL1. And what you see here, we can label the T cells, the cytotoxic CD8 T cells, and if we see them infiltrating the hydrogel, imagine this is a ball with all the microenvironment cells. So we have not only the endothelial and pericytes here, we have the cancer cells, astrocytes, microglia, and so on in the extracellular matrix, in the fibrin-based and collagen-based hydrogel. And if they internalize, it is predicted to respond. And you'll see later that when we saw that the CD8 T cells did not infiltrate, indeed, this is a good prediction to know that this patient will not respond to this therapy. And we can follow, here you can see the control is only the cancer cells are labeled, but there are all the other cell populations. And here are the PBMCs, the peripheral blood mononuclear cells that were treated with a peptide-based nanovaccine, a PLGA, PLA-based nanovaccine that is manosylated, so it binds to the CD206 mannose receptor on the dendritic cells and internalizes. The dendritic cells take them to the nanoparticles that are processed, and the peptides are expressed and presented as MHC1 and MHC2 on the dendritic cells in the lymph node, and then they bind to CD8 and CD4 T cells that move on to do their job, which is to bind to the same MHC1 complex on the tumor cells, and you can see here that they manage to destroy the cancer cells. We can follow their penetration into the 3D tumor by labeling them in a different dye, and then we can see, for example, we use it many times for ADCs that we design, antibody-drug conjugates, to see if indeed they can penetrate the 3D, or do they stay just on the viable rim that expresses, for example, an ADC with CEACAM5 targeting that is now by Merck in phase 1, bound to exatecan. We tested here to see if it can really penetrate or does it remain in the rim. So we can connect, these are the larger bioreactors, not the 96 well, and you can see we can connect 4 of them, 8, 16, and so on. And then we decided that it's not enough to have just the primary tumor, because many times we want to see the tumor-draining lymph node and also the brain metastasis. In this case, looking at melanoma, breast cancer, colorectal cancer, and lung cancer, around 60 to 90% in the advanced cases present with brain metastasis, which is a topic which is fascinating for another talk, but why do they get there? Why the blood-brain barrier allows them to enter the brain, and why do they feel so comfortable in the brain that they stay there and move from dormancy and recruit the microenvironment, the astrocytes, the microglia, and corrupt them to be allies. So to mimic this, we created, by 3D printing, a sort of a tumor-draining lymph node, where this was the design. I told you we have an architect, so this is how she starts, and then she built the STL file, and you can see how she printed it. And then each compartment got the T cells, B cells, dendritic cells, mimicking a lymph node, and this is how it looks in reality, where you have each one of the cells separately and how they interact and migrate inside the lymph node, and then we connect the whole thing between the primary tumor. Here you can see the primary tumor. In this case, it's a colorectal tumor. We connect it by tubing to the lymph node, to the tumor-draining lymph node, and then to the brain metastasis that we created. And this is how it looks in 96 well, where this is a real size of a 96. Each one gets their own supply, inlet and outlet, of microfluidics that are flowing through, let's say, every 8 wells, a different, well, everything is flown through with the PBMCs. Every 8 will get a different drug or combination of drugs that we want to test. And you can see in this case, for example, we started an 80-patient clinical trial covering 7 different indications. And we have the drugs that are the first, second, third line of therapies that the oncologist advised us that he wants to test them. And you can see here that in 2 different patients with the same exact tumor, you can see how they responded differently. This did not respond to anything. And here you can see that for each drug, it responded differently. And you can even see that, for those of you that can read the small letters, that it's not that chemotherapy in this 3D model will kill all the cells as we see in 2D culture. You really see the variability between them. Beyond the 3D the recommendations of the oncologists, we also, on the day of the surgery, we create blocks immediately, paraffin blocks, FFPE slides, and we stain them for H&E, and we run an algorithm that we developed together with Eitan Rupin from the NCI, where the idea in the beginning for Eitan was to develop a system, an AI protocol that is based on machine learning, on training with tons of slides. We are providing him all the time more and more slides. And to develop it for third world countries where they cannot use fancy staining or fish or any other, or RNA-seq and send it to Foundation, Tempus, all this. It costs about $10,000 for each one. They will not do it, so that was the idea. But in this case, we used it actually to get a very quick readout of which drugs to use for that specific patient. So it's according to the image analysis using this algorithm that looks at how well other patients with this kind of tumor, how well they responded to a certain drug or combinations of drugs. And from this is mainly for targeted therapies, not for chemotherapies. The chemotherapies we get from the patient, from the oncologists, and then on the several lines that we have left, we can test the nanomedicines that we design in the lab and see how the tumors respond. So, and then we run at the same time the RNA-seq, for example, and the whole exome sequencing of that tissue, but that takes about 10 to 12 days to get, and we treat them within 2 days, and then within 2 weeks, we already have the answer. So we develop also a protocol to freeze some of them and the PBMCs so we can resurrect them after 2 weeks and try if we have different hits for drugs to be tested from the RNA-seq. So I will give you one example with glioblastoma, how we use this system to find a new target and also how to test different drugs that we developed. So it's one of the probably most aggressive cancers. The survival is really grim. And the first thing that the oncologists advise is to go for a surgery. So they move to the neurosurgeon, we get the tissue, but at the same time, from our discussions with the neurosurgeons, we wanted to help them to create a turn-on probe that will be optically silent while in circulation. We will inject it 1 hour before the surgery, and then that it will turn on when it reaches the tumor. But reaches the tumor, it's not really scientific. How do we make it turn on? And in this case, we use cathepsin cleavable linkers like valincitruline, glyphilugly, and others to connect the dye, the Cy5 in this case. We did homofret with several Cy5 molecules, a lot of them, or Cy5 with a black hole quencher, using either a degradable, like HPMA, hydroxypropyl methacrylamide, or PGA, polyglutamic acid, that is degraded by cathepsin, and see how we can improve the survival and prolong the survival of our patients, in this case, the mice that were tumor-bearing mice. And we injected 1 hour prior to the surgery under white light. This is the black line here, and under our imaging probe. So once this nanoparticle, this or the PGA one, I'm not showing it here again, it's published, reached to the tumor just by injecting intravenously, and it will extravasate from the leaky vessels just to the area and then be cleaved by cathepsin. The dyes will be no longer at close proximity, and then we get the near-infrared light, near-infrared wavelength, and you can see here the brain metastasis, that those that survived only about 40%, and in the case after the probe, we could see that 80% of them. So we doubled the survival using this probe just 1 hour prior to the surgery. Now, beside that, it's considered a cold tumor, so immunotherapy, in most cases, maybe 6 or 5% respond to anti-PD-1 therapy, but they usually do not respond. And for chemotherapy, temozolomide is the standard of care. Bevacizumab, it's anti-VEGF antibody, or Avastin, the commercial name. It helps in terms of reducing the edema, but it does not prolong the survival. So there are very limited options for this tumor. And we wanted to look because we have the tool to look at the microenvironment, we selected the microglia, which is the immune system in the brain, the resident cells, and macrophages, tumor-associated macrophages that are bone marrow derived, but they do arrive to the tumor in the brain. And they can be found in two states, in either an M1-like, that is pro-inflammatory anti-tumorigenic, or anti-inflammatory pro-tumorigenic. And what we see is that they are being corrupted in the tumor tissue, in the brain, to move to the pro-tumorigenic anti-inflammatory. So they forget sort of that they need to attack the tumors and start helping recruiting blood vessels and growing in size. So Eilam in the lab showed that in all the tumor models and from patients, glioblastoma patients, the microglia is activated. You can see by the green. In all the normal brains, from the mouse models or from the not patients, from people that died of trauma, not from any disease in the brain, you can see that there are no microglia activated. And when we co-culture them in these spheres, the more microglia there was, the faster they proliferate, the faster they migrate. And we wanted to see who is responsible for this, so we did a proteome array and found P-selectin to be overexpressed or ever secreted. It's also in a soluble form in all of them. And P-selectin is known to be an adhesion molecule, so we decided this is a great target for drug delivery. If it is overexpressed there and not in normal vasculature, not on the normal resident cells, we can use it for targeting. And we designed, together with Rainer Haag, the first version was a polyglycerol dendrimer that is sulfonated in all the most of the end groups, and by an EMCH linker, we conjugated to paclitaxel. And indeed, we could see that if we compare the sulfated to the non-sulfated, they penetrated, internalized into the cells, the tumor cells that express the P-selectin much faster, and then they do not internalize, or internalize much, much slower, if at all, when it's just the hydroxyl group at the end groups here of the polyglycerol. Then we moved to in vivo. You can see that, again, the sulfonated accumulated preferably in the brain, in the tumor in the brain, not just in the brain generally, while the hydroxylated one, the IDCC, you can see the dye everywhere in the body and not in the brain. And this translated to nice 50% survival, which is much more than anything else, even temozolomide that we tested. Temozolomide here in yellow, this is the standard of care. So this was an option for drugs that have a functional group that can be covalently conjugated, while for drugs like trametinib, that is a MEK inhibitor that does not have a functional group, we would like to entrap it, and not only one, but two of them, a combination of trametinib and dabrafenib, BRAF and MEK inhibitors, because this is how they are approved as a combination therapy for melanoma. 50% of the melanoma have the BRAF mutation, and also for pediatric low-grade glioma, for example. So we created this sulfonated on a glycerol moiety on the PLGA. We created about 100 nanometers, very nicely homogeneous nanoparticles in a microfluidic, in a nanoassembler, and they were stable for a long time. And you can see that the more sulfate, non-sulfated, one sulfonate or two sulfonates, you can see that it internalizes faster to this 3D tumor, and the combination in the nanoparticle was much better than just giving the two drugs that have completely different half-lives. And one of the reasons is that we are forcing them to arrive together to the tumor, while the free drug in 3.5 hours is no longer in the circulation, and definitely not in the tumor. And we could use 30th of the dose and see the prolonged survival. And we see that it correlates with the P-selectin, correlates with the shorter the patient survive, the higher the P-selectin expression. So we figured out that it could be used maybe as a target, direct target for inhibition, rather than just using it for targeting nanoparticles. And to make a long story short, we saw it working in the inhibitor, again, a CAD, computer-assisted drug design, small molecule P-selectin inhibitor. We could see it working on a 3D, not in a 2D. The reason being that in 2D, they do not express the P-selectin as they express it in the patient. It translated in vivo to inhibition of tumor growth and prolongation of survival. I'll jump this. And you can see that not only glioblastoma, but all the brain metastases and pediatric DIPG and low-grade glioma, they express P-selectin, and they can be targeted in combination with anti-PD-1 that will be directed just to the tumor. And this is just how I want to end. This is a good example for translation from really basic science to the clinic. A month after we published this paper, a patient started on an antibody to a P-selectin that was just approved by Novartis for sickle cell pain crisis. Sickle cell anemia, nothing to do with cancer, and you don't need to be a radiologist to see the tumor here. It was immediately, like 2 months after we published the paper, she started the therapy, and you can see this is from October. This is a patient that was sent to a hospice 2 years ago now, and she's now back to work, and she's cognitively well. She's down from all the steroids. She doesn't need any more dexamethasone, and she was the first case. The second case, we saw reduction in the last 8 months. It's once a month injection, reduction of 84%. So this led to now a 30-patient clinical trial on glioblastoma and on brain metastasis of melanoma. So we start with the patient, we go to the biologist, chemist, bioinformatics, and back to test the compounds on the 3D models, and now we see it in 2 clinical trials. So thank you all. This is the wonderful group that actually did the work, and my great collaborators. Thank you.
Very much, Ronit, for such an interesting talk, impressive work. Really, really enjoy your talk. So now it's time for the questions. Any questions for? Yep.
Yes.
Now it's much better. Thank you. That was fantastic.
Thank you.
So my question is about that. I don't know how they are working, the 3D printers, but what I understood, what I understood is like you are taking some tumor, some part of the tumor, and then is trying to replicate. So my question is about that. How do you deal, like, when you take a tumor, the biopsy, you are going to take a part for the clinic. And then this part of the tumor is what you are trying to imitate. So I was thinking about the heterogeneity in the tumor, like how real it is, because it's not, you cannot print everything. Do you know what I mean? What is?
Yes, I know. We even published a paper where we looked by laser microdissection at different areas of breast cancer, and we could see that some are HER2 positive, some are negative, some are ER, PR positive, some are negative. And this explained many times the tumor escape following therapy with trastuzumab that targets the HER2. So we're actually selecting for those cells that do not express at the end. So we're killing only the ones that express. So heterogeneity is a known problem, but it's a known problem also just with when we biopsy a tumor, take it to the pathologist, and the characteristics are determined from that biopsy. So we are facing the same, but we are trying, if we have multiple core needle biopsies, so we take it from different places if it's possible, and then we get a mix of the cells. We dissociate the tumor to a cell suspension, so we have all the cells, including the immune cells that already infiltrated, so we could see TILs, tumor-infiltrating lymphocytes in melanoma tissues, for example, and see how they are built according to the MRI, and just scale down to be able to print 100 of them. But the heterogeneity is kept as long as the heterogeneous cell populations are in the biopsy or in the piece or the many pieces that we take, similar to what the pathologist will see.
I loved your sharing the design of your 3D printed lymph node, starting from the really pen and paper design towards the final 3D printed model. But from your images, it seemed like you made a slice of the lymph node and not the actual 3D lymph node.
No,
so
no. At the end, it's a 3D.
At the end, it's a 3D lymph node.
Yeah.
Because, okay, then...
This was just the process.
Okay.
But we see the 3D, and this is how we could see migration and invasion through the gel. Again, for that, we needed a different hydrogel that mimics the lymph node property, mechanical properties. But we could see the migration where it's needed, and in some cases, I won't show it that now, but back if you go to the patient, for example, one of them was mucosal melanoma that doesn't respond to it's a patient that had 4 cycles of ipi-nivo, of ipilimumab and nivolumab, did not respond, and we managed to see exactly the same and characterized by single-cell RNA-seq the different immune population from the lymph node. So not only the tumor, but also we got a lymphatic metastasis, so we can compare what happened before and after the treatment to see also where we can get involved with different therapies.
So your 3D printed lymph nodes are scale 1:1 to reality?
No, they're smaller.
So how does the scale mismatch?
But it's with that, it's much better than the whole tumor, because there we do like a 96 well. The original bioreactor that we printed was 1 cubic centimeter. So that was pretty realistic. But now we're scaling, it's because we wanted to be able to run high throughput, so we need it much smaller. So probably 1:10, 1:15.
Thank you.
Okay, we're running a bit late. So 2 more questions.
Yes.
Yeah. Thank you for your presentation. I was wondering, which are the sequences of the MRI you are using to gain information, and if you are using also diffusion-based sequences, maybe to tune the cell density, the features of the microenvironment that might be very useful for that.
This is super interesting. We started with T1, then T2, then we went to TRAM actually, because you see, especially in glioblastoma, you get pseudo-progression following immunotherapy, meaning that the tumor looks like it grew and did not respond, and it actually, it's more of a damage to the tissue or inflammation induced. And it's all DICOM files that we get, but we look at different protocols to see what would be the best to mimic it properly. Yeah.
Which is the way by which you select the proper cell density for each one of the cells you isolate? So how do
we sit with the radiologist to decide on that? Yeah. Thank you.
Okay, we have one question here.
Oh, hi. Actually, I've got a couple of questions. So
we have time.
I'll keep them brief.
Yes.
Firstly, when it comes to tumor disaggregation, sometimes I find in my work that the cell populations can change, or this can alter the cells. What would you recommend for that? Would you recommend doing different methods and comparing it? And secondly, when you're looking at the...
Let's go with the first.
Okay.
Before I forget. So for this, I'm standing here smiling, showing you these beautiful results. For every beautiful result, as probably all of you know, there are a lot of depressed students that work for 2 years on protocols that didn't work until we found the best one. It's a lot of try and error. It's not like the AI that we can just run and find the best one. And we see that it's different for different tumor types. So mainly different for the organ where they come from.
Okay. And secondly, when you're analyzing your 3D model for like viability and cell death, and do you find you have to make different models for metabolic assays, and what's the best way of analyzing how your drug is working, and how many different models for one patient do you need to use? And
yeah, I'm smiling because we tried all the different possible assays. Yeah. We did, it's like the Yael Naim song on, I did all the possible mistakes. So, but we learned from it, and at the moment it seems, even comparing if you look at metabolic acid, like XTT or Tighter Glow, so you can see that Tighter Glow penetrates better at 3D as opposed to thinking in 2D, they will all work the same. You see the differences. So there, after multiple assays, we decided on Tighter Glow. Okay. Looking at apoptosis, do you look at caspase or 7-AAD or annexin? Which one would be the best for early or late apoptosis? So I think that caspase would be best, and we can go on and on, but there are several that you need to see which are best for your system.
Yeah, oh, really, really interesting. Thank you.
Thank you.
Thank you. Okay, I think we are running a bit late, so we all have questions, but we can ask them in the coffee break. So let's thank Professor Satchi again.